Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
Voyager 1 has been zooming through space since 1977, but scientists never expected this. The ancient spacecraft, now 14 billion miles from Earth, just did something impossible. It changed direction on its own. Even creepier, right before turning, it started sending weird signals with patterns that scientists are scrambling to explain. NASA is staying quiet, but insiders are freaking out. Is Voyager trying to tell us something? Did it find something out there in the darkness that changed everything we know about space? The unexpected signal. In the pre-dawn hours of a Tuesday in 2023, Dr. Margaret Chin jolted upright in her chair. The 73-year-old engineer had first joined NASA's Voyager mission in 1972 as a fresh-faced graduate student. Now, nearly 5 decades later, she stared at her monitor in disbelief. Voyager 1, the most distant human-made object in existence, was sending back signals it had never been programmed to transmit. The aging spacecraft, now over 14.5 billion miles from Earth, had spent years sending back predictable data about the interstellar medium. Tonight was different. Buried within the routine telemetry was a faint rhythmic pattern, a low-frequency hum with mathematical precision. The signal persisted across multiple transmissions, ruling out random interference. More alarming was that this mysterious hum had appeared just days before Voyager made an unexpected adjustment to its trajectory, a maneuver no one at NASA had commanded. The fluorescent lights hummed overhead as Chen's colleagues gathered around her workstation. The room smelled of coffee and electronics, the same scent that had permeated mission controls since the 1970s. Though the computers had changed from room-sized machines to sleek monitors, on screen the anomalous signal pattern pulsed with unsettling regularity. When Voyager 1 launched, Jimmy Carter was president, Star Wars had just premiered in theaters, and the Apple II computer had just been introduced. Now those signals, traveling at light speed, took over 21 hours to reach Earth, enough time for a person to fly halfway around the world. What had Voyager encountered in the void? What could cause a spacecraft designed to maintain its course through the emptiness between stars to alter its path? The mission that began as an exploration of outer planets had evolved into something entirely unexpected, a mystery at the edge of interstellar space that challenged our understanding of the cosmos, and perhaps our place within it. As dawn broke over the Jet Propulsion Laboratory in Pasadena, specialists from across disciplines convened in a secure conference room. The questions hanging in the air were profound. Had Voyager 1 encountered something beyond our understanding? Was this a technical glitch in aging systems, or the first detection of something revolutionary? The answer would transform our view of interstellar space and possibly of humanity's solitude in the universe. Origins of a Grand Journey. The story of Voyager began with a rare cosmic alignment. In the early 1970s, NASA astronomers realized that Jupiter, Saturn, Uranus, and Neptune would soon arrange themselves in a configuration that occurs only once every 176 years. This planetary lineup offered an unprecedented opportunity. A spacecraft could visit all 4 outer planets in a single mission, using each planet's gravity as a slingshot to propel itself toward the next destination. Gary Flandreau, a young engineer at JPL, first recognized this possibility while plotting planetary positions on a circular slide rule. His discovery transformed what might have been separate, costly missions into an elegant grand tour of the outer solar system. The Nixon administration initially canceled the ambitious grand tour for budgetary reasons, but a scaled-back version emerged, the Voyager program, consisting of 2 identical spacecraft tasked with exploring Jupiter, Saturn, and potentially beyond. Each Voyager spacecraft resembled a large mechanical insect, standing 13 feet tall with a 12-foot dish antenna serving as its face. A long magnetometer boom extended like an insect's proboscis, keeping sensitive magnetic instruments away from the spacecraft's own electronic interference. The main body housed cameras, spectrometers, and computers with less processing power than a modern digital watch. The entire apparatus weighed 1,820 pounds, about as much as a compact car, and drew its power from 3 radioisotope thermoelectric generators that converted heat from decaying plutonium into electricity. The mission's birth was not without controversy. Environmental activists protested the launch of nuclear material into space, while budget watchdogs questioned the expense of sending probes beyond the acknowledged edge of our planetary system. Nevertheless, on August 20, 1977, Voyager 2 lifted off from Cape Canaveral atop a Titan II Centaur rocket. Voyager 1 followed on September 5 on a faster trajectory that would allow it to reach Jupiter and Saturn before its twin. Mission planners intended the exploration to last about 5 years. Instead, they created humanity's longest running space mission and our first true interstellar travelers. The engineering challenges were immense, designing systems that could withstand decades of cosmic radiation, temperatures approaching absolute zero, and the isolation of deep space. Most critically, the spacecraft needed to operate with increasing autonomy as communication delays stretched from minutes to hours. Before the Voyagers departed, Carl Sagan and a committee of scientists prepared a special payload, the Golden Record. A gold-plated copper disc containing sounds, music, greetings in 55 languages, and 116 images from Earth. Attached to each spacecraft, these records were a message to the cosmos, a time capsule of humanity intended for any intelligence that might someday encounter these lonely travelers from Earth. Planetary Revelations. Voyager 1 reached Jupiter in March 1979, beginning a period of discovery that revolutionized planetary science. As it approached the gas giant, anticipation mounted at JPL. The spacecraft's cameras revealed Jupiter with unprecedented clarity, a world of swirling clouds and massive storms. The Great Red Spot, visible from Earth for centuries, resolved into a complex weather system large enough to swallow 3 Earths. Scientists leaned forward in their chairs as each new image built line by line on their monitors, gasping at details never before seen by human eyes. The discoveries came rapidly after that. Voyager 1 revealed that Jupiter's moon Io, which astronomers had expected to be a dead, cratered world like our own moon, was instead alive with volcanic eruptions. Sulfurous plumes rose hundreds of kilometers above its surface, the first active volcanoes ever observed beyond Earth. This finding alone rewrote textbooks and expanded our understanding of geological forces in the solar system. After Jupiter, Voyager 1 continued to Saturn, arriving in November 1980. Here, the spacecraft's cameras and instruments revealed the true complexity of Saturn's rings, not simple bands as seen from Earth telescopes, but thousands of individual ringlets with intricate structures. The images showed mysterious spokes moving through the rings in braided patterns that defied easy explanation. Scientists described the sensation of seeing these images as similar to standing before a great work of art, both scientifically fascinating and aesthetically stunning. Saturn's largest moon, Titan, proved particularly intriguing. Voyager found it wrapped in a thick, orange-hued atmosphere that hid its surface from view. Spectrometers detected complex organic molecules in this atmosphere, suggesting Titan might host chemical processes similar to those that preceded life on Earth. Though Voyager couldn't see through the haze, it laid groundwork for future missions like Cassini-Huygens, which would later reveal Titan's methane lakes and rivers. The control room during these planetary encounters was a place of controlled excitement. Engineers and scientists hunched over consoles, the rhythmic clicking of keyboard strokes punctuating hushed discussions. When significant images arrived, cheers erupted, followed by intense debate over unexpected features. The air felt electric with discovery. Outside the facility, global media gathered, and images from these distant worlds appeared on television screens and newspaper front pages worldwide, bringing the wonder of exploration into living rooms across Earth. After completing its primary mission at Saturn, Voyager 1's trajectory carried it northward out of the plane of the ecliptic, the flat plane in which planets orbit the Sun. This path meant it would not encounter any more planets, while Voyager 2 continued on to Uranus and Neptune. For Voyager 1, the planetary exploration phase had ended. But an even more extraordinary journey was just beginning, the voyage into interstellar space. The pale blue dot and beyond. In February 1990, Before Voyager 1's cameras were permanently shut down to conserve power, mission scientist Carl Sagan convinced NASA to turn the spacecraft around for one final photographic assignment. From 3.7 billion miles away, Voyager captured a series of images looking back at the planets. In one of these frames appeared a pale blue dot, Earth, suspended in a sunbeam, barely visible among the vastness of space. The resulting image became one of the most profound photographs ever taken. Sagan later reflected that this tiny pixel, our entire world, illustrated our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. The photograph transformed scientific data into philosophical perspective, showing humanity's place in the cosmos with humbling clarity. After the pale blue dot portrait, mission controllers commanded Voyager 1's cameras to power down permanently. The camera platform had served its purpose. The future journey would be tracked through invisible fields and particles rather than images. This symbolic moment marked the transition from Voyager as planetary explorer to Voyager as interstellar pioneer. The spacecraft's power supply, its radioisotope thermoelectric generator, continued its inevitable decline, producing about 4 watts less electricity each year. Engineers compared it to a flashlight slowly dimming over decades, yet they kept finding ways to read by its light. They implemented creative power-saving measures, shutting off heaters and non-essential equipment. Systems designed to operate at comfortable room temperatures now functioned at near-freezing conditions. The spacecraft's resilience surprised even its creators. As Voyager 1 traveled beyond the orbit of Pluto, still classified as a planet when the mission began, its instruments recorded the thinning of the solar wind, the stream of charged particles continuously flowing outward from the Sun. This region, called the outer heliosphere, represented the fading influence of our star. Scientists eagerly analyzed each transmission, watching for signs that Voyager was approaching the boundary where our Sun's domain ends and true interstellar space begins. The data downlink rate had slowed dramatically since the Jupiter and Saturn encounters. Where once Voyager sent 115,000 bits per second of planetary images and measurements, it now transmitted at only 160 bits per second, slower than the earliest home internet modem. Each precious bit of information traveled across billions of miles, captured by 70-meter dish antennas of NASA's Deep Space Network. When these signals reached Earth, they were so faint they were measured in septillions of a watt, yet they carried crucial